To the Astronomy Club of Akron October membership meeting, and I'm very happy to introduce our guest speaker, Dr. J. Reynolds. Dr. Reynolds is a professor in the physics department at Cleveland State University. He's been out to talk to us several times at our membership meetings. He's been out to our observatory and gave us a presentation at one of our telescope seminars. So let's have a hand for Dr. Reynolds.
Thanks. I have to ask you, what the heck are you doing in here today?
I know.
See you, yeah. Better make it good.
Yeah, better. Take off my shirt. So, anyway, yeah, what a gorgeous day and a gorgeous week we have coming up here. All right, let's see. Okay. All right, yeah, I'm with Cleveland State. Not for much longer. We're having a fire sale coming out here. Anyone want any, I think they have washing machines and sewing machines as well. So yeah, just like all the universities, we're all in trouble, and Cleveland State is not exempt. So I'm probably going to retire, or I don't know. We'll see. I'll let you know. So anyway, also like to promote WKYC Channel 3, our NBC affiliate. They help produce In the Sky, and In the Sky is a little TV program I do along with my co-host Gail Franco. And so we've been doing this for a little while. So obviously we talk about what's going on, but try to take a different spin on it here. So this is our 9th year. We're about to finish our 9th year and starting our 10th. Yeah, it's exciting if you think about it.
When's it on? Yeah, when is it on? When's it on?
It started off on analog TV, and then they decided they wanted to pair it all off, not just on a schedule, but also online, because Tegna, who owns Channel 3, said, you got to start developing local programming. So I was the first one they came to, because they know I'm a sucker. And so they said, can you do this? Yeah, okay. So there was a schedule. It was on the weekends, particular time, particular slot. But then they started pairing it into social media. So I never know where it's at, but there's something called Weather Warriors, the Facebook site. It's pretty busy. I'm surprised, but yeah. So it's always on there. That's where the bulk of them are. But so for a while we tried to promote all the clubs and their telescope nights. And we found that the ratings for that was very poor. Only because, if you think about it, if we're promoting Akron, the people in Cleveland don't care. If we're promoting CAA, well, then the people in Akron or even the East Side don't care. So the ratings went really low down on that, and it didn't seem to be effective. So anyway, but for big events like the solar eclipse, we were going to do that, but then we realized all these huge organizations, Great Lakes Science, NASA, they were promoting their own events. There's no way we could overshadow any of this stuff. So anyway, that's what's going on with us in there. I'm also a member of Cuyahoga Astronomical Association. We cover mostly Cuyahoga and Medina counties and some Lorain County along with Black River. We're meeting now at Baldwin Wallace. We have a partnership with Medina County Park District where our observatory is, and I need to delete this because we deleted our partnership with these folks. Folks, if you ever want to do something with Cleveland Metro Parks, good luck. Oops. They're tough. Even one of the managers 7 years ago for the 2017 eclipse, they said, don't work with us, we're terrible.
Yeah, it's hunting a little bit. If you could stay like in this area.
Right here, okay.
Whether
yeah, but then they can't see.
Well, or in back of the table.
She throws stuff. She's already doing it.
I want to take pictures.
Oh, okay.
It's just doing a little hunting with the lights off.
All right, well, yeah. Anyway, with CAA, we do 11 public lectures. We have only 6 star parties. We could take a lesson from Akron here because ours are very scheduled, and if it's pouring down rain, we cancel them, and that's no reschedule, no rain date at all. But This year, boy, we've had 6 really good ones because, you know, the weather was so good. And also, we do a lot of tremendous amount of outreach, sometimes maybe a little too much. This year was the big year. I can't tell you how many things we've done. We were always, like every weekend, going here, going there, not just schools, libraries, but other parks as well. We just broke 156 members, so that's a record for us. I know Akron has been as high as 200, but these are dues-paying members, so we're very proud of that, that's for sure. We served 70,000 people in the last 20 years, and that's all free. So, and that's going elsewhere, like I said, the outreach component. So our biggest event is the solar eclipse in 2017. We had 10,000 people at Edgewater Park. So,
Wow.
yeah, it was a good day. Good thing we had a lot of scopes out there, you know.
Was it fun? I bet it was a fun crowd, wasn't it?
Oh, it was, yeah. It was good, it was good, so. And we had a lot of other people bringing out scopes. So, who's that guy? I don't know. You know, so anyway. This is our location called Letha House Park in Medina County here. This is our observatory. We only have 3 telescopes and they're all really small and cute compared to your 16-inch scope. So, but anyway, it's small, it's good. And so we teach it, we utilize this as like a lab. So we close the door, we let maybe 8 people in. They have 3 different views in 3 different scopes there. And if there's enough time, we let them drive the scope, or I should say, like wander and control, like if they're looking at the moon or some star field like that. So it's real hands-on for them, as opposed to being outside here. The members, of course, utilize their own scopes, and we let a lot of people out there. We've had as many as 150 people out for our telescope nights there. So very nice, a lot of fun, very nice. They bring kids. We tell them, don't bring the 4-year-olds. Why do they bring the 4-year-olds? They bring a dog. No, that dog wraps itself around that tripod. You're not gonna like the bill.
How long is that scope right there, Neil, that big white one?
Yeah, what about, that's called a refractor, sir.
How long is it?
That's what she said.
Yeah. Thank you.
No, I think that's a 6-inch scope. I don't know what the length is.
That's impressive.
Yeah, it is. And this guy here, he has, we call it the telescope museum at home. He has so much stuff and he gets rid of nothing. He's also a bachelor.
Collapsible?
Yeah.
That's how you transport.
Is that collapsible?
Well, well, buildable, yeah. This goes in the car separately.
Oh,
This goes in, the
apart.
mount goes separately. Oh, yeah, it takes them a half an hour to build the thing. What was fun was, we used to do programs on the grounds of NASA, and when he would show up with the great big hollow tube on top of his car, security would say, what the hell are you bringing?
Bazooka.
Yeah, exactly. Cannon, artillery. Yeah. Also, in the observatory, I brought this out here. People ask me, what's this for? Do you have a hip problem? No, not yet. But I've been using this for about 8 years in the observatory, but also a little public. I live in a condo association where you don't have to be over 50, but everyone is. So it's like 70, 80 years old. But I have this, and the idea is put this out. You know how everyone likes to grab that eyepiece there? Let go, kid. Well, have them lean on this. And it's so portable, it's lightweight, you can move it around, lean on this or lean like that. It's perfect. People love it. And you can move it in, you can move it out, whatever. So I thought I'd just bring down a little tip. $10 at Goodwill, can't beat it. Seriously. Anyway, just a thought. So our members are starting to buy these as well because people are complaining out in the dark when they're looking through the big scopes like that. It would be nice to lean up against something like that. So anyway,
Clever.
yeah, and cheap too. So also something we instituted about 3 years ago, 3 or 4 years ago, is telescope help. You know how people bring out old scopes? Can you help me with this? Yeah, you're missing this. What's this for? You look through it. And so anyway,
You at the comedy club too?
Yeah, he does.
Yeah, it's funny. A lot of women, I'm a bachelor as well. A lot of women say, "Oh, he's so funny." Well, after about 20 minutes, I'm getting away from this guy. So, yeah, definitely. But the whole telescope help thing, what we do is now, instead of people just randomly bringing out scopes, we tell them, if you have an old telescope that you want us to help you with, or if you just don't know what to do, bring it out an hour ahead of time while it's still daylight, okay? Some lady brought it, and it was like 9:30 at night. I said, no, well, can't you help me? No, I can't see it. Okay. But my point is that we've instituted that as a recurring thing. Every telescope night, come on out an hour early, bring the scope, and our members set up their scopes and get that done, and then start working with the public. It has become so popular with the public. Every session that we have, we probably have 3, 4, 5, and we get new members out of it too. Definitely, it's a wonderful thing that we're doing, and it's we're going to keep on doing it. So anyway, just a
Good.
tip, yeah, something. Trying to do that outreach, help the folks with. So all right. Well, let's talk about neutron stars. First of all, they're not really stars. Not in the classical definition of neutron stars. Now, a lot of you already know a lot of this and probably do a better presentation than I could. This talk is really meant from kind of the ground up, if you will. So neutron stars are, I could do a whole semester on neutron stars alone, and black holes, the whole 9 yards. Oh, and don't you love it when people say, come up to your telescope, can you show me a black hole?
That'd be a boat.
You just want to either say, think about your question before you ask that, or just move the scope to a dark area of the sky. There you go. You're done.
There was one near Saturn last night.
A black hole?
Someone saw a black hole near Saturn last night.
Nice. Oh, good. Good. Nobel Prize right there, man.
There.
So most of you are also aware about temperature and size differences here. We have small, cute little red dwarf stars here, K and G, and yellow stars like our own sun, and the great big hot blue ones like Sirius, very high temperature and blue color. And I love to show people, especially in your 16-inch scope, it's nice when you have a big scope you can show stars really do have color. It is amazing color there. This last telescope night, we were showing Alberio in a small scope. Then, in a smaller scope, Ron and I, we were talking about that super wide eyepiece. Well, we were using a refractor with a wide field, but on a refractor. So we were able to get the whole coat hanger in there in one shot. So you look at Alberio, oh, that's nice, and then suddenly you have all these hot blue stars like this in the shape, and every single person said, oh, wow, that's great. You know you got them when you get the oh, wow like that. So anyway, stars do come in colors, but that will be our last reference to colors. So when we look at the mass of stars, because we do have to talk about that aspect, because when you talk about anything in the neutron star range here, so low mass like our sun here, intermediate masses, 2 to 8 solar masses, basically multiply that against our sun, and then high mass stars over 8 solar masses or something. Okay. Very quickly, we've all probably seen this before. I would love to know the person who put this together. I've never seen the credits for this at all. But the bottom line is, here we have our solar system. This would be the size of the Earth. Cute little Pluto, probably the most interesting celestial body in our solar system. And when we start to look at the size of our sun compared to everyone else, it's really quite large, but not compared to other stars. Jupiter, right here, this cute little dot there. Here's our sun compared to Sirius, the dog star, and Pollux. And of course, we can't forget Arcturus as well. So you can see our sun is not the dominant dot here. So if our sun is a dot, of course we look at Betelgeuse or Betelgeuse. Don't say it 3 times, you know what happens here. And Ceres, this big one here. Okay, so what does all this have to do with neutron stars? Well, quite a bit here. Of course, we have the Pleiades right down here, main sequence of typical stars. Some last a lot longer than 10 billion years, like our sun here. Some are 20 billion, some are 3 million though, okay? So if you notice, one mass equals 10 billion, two masses, 1 billion. Yeah, your life expectancy starts to go down, okay? Hopefully you have insurance. 30 mass, okay, and you're now down to 3 million lifetime years, that's it. So short lifetime of massive or supermassive stars like this. And especially blue stars, the hot ones, they don't last very long at all, like the Pleiades. Beautiful photography of the Pleiades, and it's out in full force. Love to see that, one of our favorite star clusters, of course. Okay. All right, so what do you get when you run out of gas? Well, you could say gas or you could say fuel, call it whatever you want here. You get white dwarfs, like our sun will eventually become a white dwarf. So if we look here at the beginning of a star, protostar, and then the main sequence, like our sun is here. But this is a rendition of a low mass star, unlike our sun. The sun is more than this, but it goes from main sequence to a white dwarf. That's it, small, cute, that's it. And lasts a long time in the process. So at the end of a life though, if you think about it, especially like our sun here, our sun looks like this, yellow. Eventually, as we begin to run out of the hydrogen fuel, our ability to fuse hydrogen into helium will then cause an upset stomach, basically, and our sun will begin to grow to a very, very large and expand in terms of size, almost out to, well, at least the orbit of Mars is what is thought, okay? So it's going to expand. Here is what we look like today. This is how we're going to look eventually here. The sun is a red giant. This is a very temporary state here. And inside the star, there are two forces. Of course, you have gravity wants to collapse the star, but you have a lot of heat inside the star, forcing it back out, balancing things out. But as radiation is trapped more and more, it releases, okay? But when the sun begins to run out of hydrogen, it wants to collapse down, and then things begin to be upset. As we currently have an upset star called sunspots, okay, and all the northern lights, eventually it begins to emit a lot of material into our solar system and causes it to expand more and more. And so these outer layers expand outwards, causing the red giant, and then at the end, just like here, we get a white dwarf. And so, curious, how many of you have seen this central star of the Ring Nebula? Yeah, show of hands. Not that many, yeah. Because it's a white dwarf. Conditions have to be just perfect to see this. How about the pointer star off to one side of the Ring Nebula? Yeah, for almost anyone can see this star here. A small telescope reveals it pretty well. Quick story, especially if you deal with a lot of people here. I had 6 students in my research observatory over at Lakeland Community College. And so we were up, they had never been in front of a telescope. This was kind of an outreach thing. So as we came out, it was about midnight, and the Ring Nebula was directly over us, and I said, wow, we should be able to see the central star. They had no idea what I was talking about. So we look inside there, they certainly saw this, and they saw this. They said, okay, so what's the big deal? I said, hardly anyone ever sees this. This is a big deal. So suddenly, I had 3 guys and 3 girls in there. And suddenly, they said, I think I see something else besides that. And I said, well, all right, instead of describing it, just draw a circle and put dots when you see stars, okay? Don't show me and don't show anyone else. Okay, fine. So at the end of the exercise, I said, all right, raise your papers. And so what they had was, of course, the pointer star, the central star, and these 2 as well. And I'm like, you gotta be kidding. And I said, so I brought up the same photo right here. I said, this is what you saw. And they had it perfect. The 3 that could see it were girls, and the 3 that could not were guys. So visual acuity of females is usually better, and certainly the color palette is much better, because I prefer green versus turquoise and all these other colors. But isn't that amazing though? I certainly will never see these at all. Conditions were absolutely perfect. The eyepieces, everything just came to be. So truly amazing to see.
What are those dots?
I'm sorry?
What are those other dots?
Oh, just stars on the other side of the,
The other side?
yeah, that's it. Yeah, yes.
What was the focal length that you were looking at?
Yeah, it was only a 12-inch scope. That's the amazing part. So it was what, no, it was like 2,300. Yeah, but we used the right combination of eyepieces as well. You know, that's critical right there. So it was perfect. But perfect conditions, perfect dark sky, et cetera, et cetera, et cetera. So, you know. So anyway, as just like here, all the energy, everything's pushing away here, and eventually you get this with no fuel available. The core begins to cool off and becomes what's called a white dwarf. So this shrinks very, very significantly. So imagine taking a large star or a large mass like our star and shrinking it down to about the size of the Earth. Highly compressed, highly dense, and also very, very hot. All that compressed right down through there. So you get a white dwarf all by itself. Cute. So our sun has that to look forward to. Okay. So burned out cores of stars shrunk to about the size of the Earth here. Okay. Very dense and roughly 1,000,000 times greater than that of our sun because of the density factor. Okay. And of course, the gravity of a white dwarf is very high, over 100,000 times that of the Earth's. So that's a white dwarf. And if you have a chance to have a look at Sirius A here during the winter time or early morning hours, you might be able to see this white dwarf down here, Sirius B. And this is it. It's a white dwarf star. Some people, if you have the right configuration, you can see it. But again, this is what our sun is going to do at some point in the future here. It once was a major star at one time, swelled to a red giant, shrank to a white dwarf, and of course, they cool and fade away as they age. So they were able to rewind the whole idea on Sirius B based on the mass of the star, current temperature, current mass. Temperature is about 25,000 Kelvin. That's really high. Estimates are that this star, about 120 million years ago, was a regular star. So that's what we have to look forward to. Kind of cool to see that. And of course, central star in M57.
How much time does the Earth have?
Yeah, well, you know, about 4 billion years.
4 billion? Okay.
Yeah.
I feel good now.
Yeah, so. Since this is political season, I should make a political joke, but I won't.
Yes, no, go ahead.
No. Depends on who you elect.
I don't want to start that.
Yeah, that's right. But here we have this, usually in photographs, you can see this galaxy next to M57, but sometimes in a telescope. How about the 16? Have you ever tried that? No?
I haven't seen that.
No, okay, I wasn't sure. I mean, with the 16, that's, so what do you need to make a neutron star? Any idea?
Neutrons.
What do you need to make
More
And what are
mass.
neutrons made of?
More mass.
Ding! Give that man a cigar. That's right. So lots and lots of mass here. So started off with a nebula protostar, and notice here a color difference, main sequence star, but this one's hot blue and not going to last very long. Kind of like the Pleiades. Eventually, the Pleiades is going to pop like popcorn into supergiants, red supergiants here. And before you can be a neutron star, you have to take all that mass, collapse it down, because mass equals energy. So if you have more mass, you have more potential energy to convert, possibly into a neutron star or a black hole. That's right. Okay. So, but we clearly have a black hole very close to Saturn here. So, okay. So black holes, in this case, this is a supernova. 1987A. And you would think after the supernova, it's only 168 million 168,000 light years away from us. It's actually very close and has been studied, but guess what? We can't find a neutron star inside of here. You would think it would. So did it become a black hole? No, it doesn't seem to. Did it become a neutron star? No, it doesn't seem to. So did it blow itself out? Yeah, maybe so. Okay, so yeah, this is in the southern horizon, and so we can't, southern hemisphere, we can't study it up here, but still very cool. So this first supernova visible in the last 400 years. We can't find the neutron star. They've looked, and so the core collapse during the explosion may have disrupted the formation of it. So it should result in a neutron star, but it didn't turn out that way. Neutron stars are typically, this is not a typo, maybe the size of 12 miles. Think of the Earth with a white dwarf, neutron stars, higher mass, collapse down so much more, down to about the size of Manhattan. Think about all that. So if you collapse something that much, temperature's going to be higher, pressures are going to be much higher, and also the gravity is going to be off the charts here. So all in a tiny space the size of New York. So maybe that's what happened to Manhattan, okay? The density is very, very high. Think about all this mass in a tiny sphere, that's all. So extreme pressures on the top and inside, to the point that, yes, everything's made of mostly neutrons because nothing else can easily survive. Lastly, inside the material becomes, because the pressure's so high, becomes like a superfluid, which also occurs in Jupiter because the pressures there are also so high as well. And the surface of a neutron star tends to be solid because the pressure, temperatures and the pressures are lowest there. And lastly, composed of extremely dense form of iron. So it's truly amazing when you think about it. So how do we study these? It's tough to study neutron stars because they emit their energies. Like our sun emits a lot of energy in the visible portion of the spectrum, also in X-ray, gamma ray, infrared, a lot of infrared, and of course ultraviolet, which is our friend during the summer, and it gives the sunburn. But these neutron stars, full spectrum emissions, but anywhere from radio to X-rays. Well, it's nice, but here on Earth, we have a tough time studying ultraviolets, gamma rays, X-rays, because our atmosphere protects us here. So it almost requires us to be out in space, which means Hubble Space Telescope can do some stuff, James Webb can do other things like that, because it's outside of Earth's atmosphere. But radio is pretty easy. Do you have someone doing radio telescope here? I thought so.
Jim
Yeah.
Watson.
Oh, Jim, what bands are you looking through? No?
Jim,
No.
he's hard hearing.
Oh,
Jim, your radio telescope,
Yeah.
what's your frequency? 12 gigawatts or
50
gigahertz?
radio telescope is 11 gigahertz.
Okay, all right, okay. It's still up there, compared to the ham radio folks, so, yeah. So anyway, as we know, we found, do you ever listen to any pulsars at all?
Pulsars? Did you ever get a pulsar?
You know, it's a 19-inch F-24.
Okay,
The focal length.
okay.
The source, did you ever listen to a pulsar?
No? Okay, all right. I think down in Youngstown, they have a radio guy down there as well. And so I think he's been successful at some way. He likes to listen to Jupiter, because Jupiter, as Io is passing through the electromagnetic sphere, it makes a lot of creepy stuff. I played it one night in my house, and my daughter came out of the bedroom. She said, "What is that?" Because it scared the crap out of her. And so I told her what was going on, and she said, "You're not allowed to ever play that again." And she went back to bed. I said, "Okay, I get it." So, all right, so some pulsars, believe it or not, and I'll explain all about that, have been discovered pulsing in not just radio waves, but also in X-rays as well, and in the gamma spectrum. But oddly enough, those same pulsars, no radio signal. Very odd. This is the Vela pulsar, but this photo was taken in the X-ray spectrum outside of Earth's atmosphere here. I think these are both Hubble, and also the pulsar at the center of the Crab Nebula. Again, Hubble Space Telescope, and excuse me, no, the X-ray, Chandra X-ray Telescope took these too. So neutrons do something else very cool, very different, okay? And pulsars, yeah, so first of all, 1967, Jocelyn Bell detected the radio signal with a rapid pulse rate. And as a result, what she discovered was a pulse rate of 1.3 seconds for a pulse width of 0.04. Let me play that for you. This is what Jocelyn Bell heard in 1967. She was the first person to ever hear this. That is a neutron star rotating. Think of something the size of the Earth, or better yet, the size of Manhattan, rotating that fast. Anything on there, you would think, well, it would just fall apart. No, no. So much gravity there, so much mass. It all holds together just fine. And so it's not just the frequency, the how often it, but also the width, how long the is there. So she was the first person to pick that up. Okay. Eventually, she was awarded, well, her advisor, the guy who really, who was in charge of the research, he earned the Nobel Prize for detecting this, but he directed her and set everything up. But so there was a big outcry because, well, she should receive that. Well, maybe not. Anyway, she was the discoverer of this particular pulsar here. So, is it really a star that pulses? That's the question. In 1967, they didn't know. They didn't know. So, how would it pulse? Would it just emit like this? I don't know. So, okay, so they have to start looking into this. So they start looking for more things like this. So that pulse was not very fast, not very frequent. You would think if it's a star pulsing, it would pulse more, especially like a neutron star. Maybe this is a white dwarf pulsing. Maybe it's rotating because everything in space rotates, everything. Okay, put you in space, you rotate. Within a couple of weeks, you're rotating in some manner. It may be goofy, but you'll be rotating. Every asteroid rotates. Every star rotates. Everything rotates. Some things rotate very quickly. We've seen a few stars that, forget which star it is, but anyway, the actual image itself shows that its rotation is fast enough that it's kind of elongated at the equator. So if something rotates, it could be a white dwarf. Yeah, but the white dwarf can only rotate so fast or else it'll start to fall apart. So I don't know. It's very slow for that rotation period here. When they started discovering other pulsars, they had much shorter periods, okay? And I'll show you a few of those in a second here. So they found more pulsating radio sources, but eventually they were called pulsars. And if you're old enough, you may recall when the term hit the mainstream news here. So again,
any of these visible objects?
oh, I'll get to that. Like one of my students. Yeah. So ordinarily, if you think about it, pulsating variables, if it's rotating, the period density, if you think about it, period, how long it takes to go one time around, and the density of the particular star. Because if the density is too low, then it's going to fly apart. So that enables it to go faster if it's more dense here. So when you take the period here, the square root of the density, so it's very proportionate. So if you hear the density, the pulsing period here, you can begin to make some very good mathematical assumptions that here's the density of the particular object that we're listening to, okay? So you can see on some of these pulsars, it's really quite fast. 1 second here, like so, okay? So when we look at these, they're not a pulsating star itself, like our sun does not pulse, okay? Our sun rotates about once every 30 days, depending on how you want to measure it. So some are rotating neutron stars based on the numbers here. So we know this because, as an example, if we take our sun, which has a certain amount of mass, and we know what that mass is here, and rotates in a 30-day period, if you start rotating it faster and faster and faster, it's going to fly apart unless it has enough gravitational pull to keep it all together. So if we take the same mass of our sun and begin to compress it, let's say there's a big monster that can compress this thing down further and further and further. Okay, well, you have the same mass, but it's compressed more. As our sun rotates every 30 days, if you compress it more, the rotation is going to begin to increase faster and faster and faster and faster. So if you take that and compress it down, you could go as high as 1,000 times a second, but the mass is not sufficient to stay together like this. So compressed to the size of a neutron star, the size of Manhattan, our sun just wouldn't work because of the lack of mass, but you get the idea. So compress it down, it's going to rotate very, very fast. So when you hear these pulsars, you get the feel, you get the understanding how massive they truly are. So, all right. When you compress, or let me come back here, mass, velocity of the rotation, and the number of rotation here. So just like a ballerina, as she rotates her body around and around, as she brings in her arms like this, the rotation period increases almost exponentially here. Same thing with stars like this, okay? So where does this commission come from, okay? This emission, don't forget there's a lot of magnetic fields. Our sun exerts magnetic fields, and we can tell just by looking at some of the hydrogen alpha scopes that we have and the sodium scopes that we have here. So magnetic fields are just bursting all over the sun like this. Well, on larger stars, more massive stars, the magnetic field is even more powerful. And so it begins to form up a beam of energy coming out based on the magnetic field, like a flashlight, and it becomes very focused very quickly, so it can actually emit in a front and a rear direction, depending on its rotation. So if you think about it, beam to radiation, rapid rotation or rapid spin gives you this observed characteristic, kind of like a rotating neutron star, okay? So you have this beam that crosses the Earth, that's all. So as it sweeps by, just like a lighthouse. So you have not just how often, but how long. So you can tell a lot about the star, also about the lighthouse as well. So, and this is the same thing. So as it rotates, we can then look at the frequency, but also the width as well. So, okay. So here's some pulsars, which is really amazing. This particular pulsar, they're called millisecond pulsars. If you think, so you listen to this. .4 rotations a second, the size of New York. It has to be well put together. So really, think about that, okay? So it's rotating very fast. This is the Vela supernova, 11 parsecs away from us, but here we come. All right. That's incredible. And it all stays together because there's so much mass in one place.
What causes the noise?
The energy that's coming out, if you listen in certain radio bands, or
Thoughts of.
yeah, that's it. And the Crab Nebula, a little. And it's right in the heart of the crab. It's hard to identify where the source is in this Hubble photograph here. You have to have like the Chandra X-ray telescope, and that will show it just pops right out because there's so much energy there. And lastly, 642 rotations per second.
Almost continuous.
That's amazing.
Amazing.
And how big was that, how big is that star, do they think? The
Yeah.
size,
That's
mass?
about the size of Manhattan.
642 per second.
No less massive than a couple of Earths, right? So,
And nothing comes off the surface?
Nothing. No. Light does, but that's only because of the velocity. But still, you're red shifting that off. Yeah.
Do they stick a big radio telescope like the Green Bank things, or smaller ones to pick those up?
Well, actually, the first one from Jocelyn Bell, that was a small deal. Then I think Ohio State was trying to do some stuff down there. I don't know how successful. It helps to have, well, bigger antennas to detect these. So I don't know who's doing the detections these days with radio telescopes, or if the pulsars are really their target. So, yeah. But what's nice is when it's cloudy, yeah, just turn on the radio.
How regular is the rotation? Does it drift like from 641?
I'm getting to that. So neutron stars occasionally speed up. How about that? How would they speed up? That doesn't make sense. Well, think about it. If you have a certain amount of mass, a certain rotational speed, okay, that's fine. But what happens if you partially lose mass, but more importantly, if things you lose enough mass that you lose stuff off into space, flung off, so therefore your body becomes a tiny bit smaller. The rotation speed will actually go up and it will actually increase. Yes. So instead of 642, it might be 642.1. So, but yeah, they do that. So they can crack and make the radius smaller, therefore the rotation numbers go up and speed up. But, so that's the happy part about them. But eventually these will die, okay, if you think about it. Eventually they expect to slow to a point, and don't forget, they're very hot, and they cool off as well. But at some point their emissions become undetectable. And this is gonna take a very long time, but eventually the pulsar, it doesn't really die, it just doesn't emit these signals anymore. So this is a temporary thing, but very long term. So anyhow, amazing just photography of this, but this was also an X-ray, okay. So more recently, they found a white dwarf in 2016 that is a pulsar. It rotates, it has a magnetic field, it has enough emissions because there's a heat source inside of there cooling off, and therefore its emissions and the magnetic field focus enough energy outwards that they made detection. This was in 2016, the very first one, okay? And since then, they just found a second one, last year, as a matter of fact, so. Kind of cool. Didn't expect white dwarf pulsars. Always thought they were going to be neutron stars. So, anyway, finally, I just want to close with the following here. We're at 250, but very famous words by Carl Sagan. We accept the products of science, but not its methods. Well, here at this group, I'm speaking to the, you already initiated. But when I speak to my students, they're all sitting there with their iPhones and stuff like that, and I get that, but they don't understand or don't employ scientific method or objectivity. Whereas a group like this, in order to be successful, you must be objective. You must employ scientific method, regardless of what you're doing. And so that's how we measure, gain success. If we listen to these words and really take them to heart, I try to impose that, not impose, but show the students the benefits of thinking logically. So many people do not, okay? When we look into our heavens more and more and learn so much more all the time, it becomes amazing to think about what we don't know. But objectively, we're learning so much more, but also utilizing the scientific method. If our world could do what this club does and become a light and carry this light of scientific objectivity, scientific method, and taking our time, but analyzing and becoming part of the process here. It's just like taking that one light and passing the light along, just like candles here. So I want to thank everyone for your attention today, and I guess I'll have questions. That's it.
Is a black hole really a hole?
Find a hole.
Well, a hole's something you go through.
Yes.
It's in a fabric or
Yes.
plane of some sort, you go through it.
Yes.
So
But
what's
go
the
through
plane?
it. Yeah, so once you go in, you're not coming out. But at the same time, is it like a hole itself? Well, you could, a hole, we think of it as 2 or 3 dimensional, where it's a flat opening here, and no matter where you're coming in from all three dimensions. But still, if you go in, you're not coming out. So it is technically kind of a hole, yeah.
But what's the surface of the hole?
Nothing,
Nothing.
no. Just don't go near it, okay? Stay away from it.
Good advice.
Yes,
Go ahead.
So I was gonna ask, so, you know, pulsars have a beam that comes out that has some conical shape to it.
yeah.
And we found some. Does that mean they're just as many,
Yes.
zillions more in the same proximity to us?
They're
that
just
we
not-
haven't seen because they don't shine on us?
Right, they're not shining on us, exactly.
Oh, is it?
Give them a buck. Anyone else? Yes, sir.
First, it's kind of encouraging to see new things discovered in latest 2016, that observational astronomy still has a place in the world.
Yeah,
Second, something I just don't know, when you say the sun, when we know, we say the sun's gonna last so many million years, I know that's done from the calculation of physics, but can we observe the hydrogen-helium ratio to confirm that seems to make sense? That the sun is converting helium and hydrogen at the rate we think it should?
we can, but also, if you use spectrographic information, that'll also add, don't forget, it's not just one view or one science, it's a multitude of sciences coming together to make these predictions, okay?
But they're not just from the physics, they're from actually looking at spectrographic.
Absolutely, yes, because you can see all the calcium lines in there,
So
just
we
see
can do that
everything.
for other stars too.
Yes, yes. So our sun is a great role model, but then we have, don't forget how many stars we have pretty close to us too. You know, we have Sirius A, Sirius B, great models, white dwarf right there, a nice hot blue star, oh gosh. So we've learned because of our models here. Yes, anyone else, please? Yes,
Yeah, you said that a neutron star eventually just becomes neutrons. I mean, are there protons here? And assume the electrons are long gone.
right now at this point, but as things cool down, we can start to theorize that you may see reemergence of some of those. Because don't forget, yes, in the center is all neutrons, but towards the top, you have very high temperatures, you have high pressures and high gravity, and so you're able to have iron. So is that iron like what we're used to? No, it's a different type of iron, but still you have iron molecules there, and not molecules, but atoms starting to set up. So could it re-emerge into maybe having electrons and protons? Mathematically, I guess it does, but yeah, we'll never see it. So, anyone else? Anyone else not had a chance yet?
I was gonna ask his next question.
Dude, that's, I give you $100.
I was gonna ask, so a neutron, the frequency that's emitted by a neutron star is just one spot on the electromagnetic spectrum. Are there neutron stars that emit their cone of frequency, whatever, in visible light ranges?
Yes. Invisible?
No, visible light.
Yeah. That I'm not aware of. I'm just aware of the neutron stars are very active in the X-ray range, okay? And so having them actually in visible spectrum, I'm not aware of any of these. I'm not an expert on neutron stars. What I do tend to study is I used to be on the Dawn team for and also the Deep Impact mission for asteroid research. That's really my expertise, but still. So in the visible spectrum, I'm not aware. Anyone else? Yes.
We were all kind of curious about this nova that's supposed to go off T Cronus Borealis.
A little bit louder,
What?
a little bit louder.
Louder, Ron.
We can't hear you.
I say we were all curious about the nova that's supposed to go off, T Corona Borealis.
Yes.
And that's, the mechanism for that is you have a white dwarf with a red giant next to it, and the material is being drawn off the red giant into the white dwarf, into an envelope, and then that mysteriously goes to a nuclear flash and gives us the nova. A very similar mechanism for a type 1A supernova, where the material is going onto the surface and then increases the mass of the white dwarf, and then we have a supernova explosion. Two totally different results, yet the mechanism is very close to the same.
Very close.
Could you tell us what the difference in the mechanisms are?
Well, I have a very brief, I have a few graphics here. Hold on a second. Let me get it right. As you asked. Okay, so binary star is next to a binary pair. It's called a recurrent nova here. 3,000 light years away, constellation in Corona Borealis. I have a map for you. So this is when this does happen, and we've been reading about it basically this whole year. We'll see it to a magnitude of maybe this particular star is at magnitude 10. Not easily seen. Good telescope, and it's really very unimpressive. Okay, so but we've seen in the past, in modern history, outbursts have been witnessed twice, but actually it has happened more frequently. This particular star, again, when it has this outburst, we'll get to approximately magnitude 2. Think about that, magnitude 2. Okay, all right. Or in this case, back in 1946. Magnitude 3. Very unimpressive, easily overlooked. Okay, everyone's expecting to be, playing dodgeball in their backyard when this thing goes off. It's not going to be bright enough for that. But still, if you know where to look, take a before and after picture. And if has anyone taken any photos of this constellation? Oh, okay, yeah. So you're after the before and after. You know this is going to happen when it's behind the sun. You just know it. They were so wrong on it. Oh, it'll be in April. Okay, May. Okay, now it's the fall. Okay, yeah, you know it's going to be January. So it might even peak at magnitude 2.5. We'll see. So 1886 and 1946. Okay, so 120 stars are much brighter than this thing can get at this point. So is it impressive? Yeah, sort of in a way, but not really. But think about all the cool stuff that we have seen here in northeastern Ohio this year, with the eclipse, the northern lights, etc. A comet. The comet wasn't that great, but still, it's a comet that we were able to see. So all right. So maybe this thing will not let us down. Hard to say. All right. So here's the chart. here's the constellation, and it's not a great one. That telescope you were talking about with the wide field, yeah, boy, that would be nice to have this whole thing before and after like that. So the star in question will be right here. So normally you don't see it unless you know what you're looking for. So that's where the action is going to take place at some point. Maybe not even this year. Hard to say here. So okay, fine. It's supposed to happen. This large, cool or a red giant star and the white dwarf, which is much hotter, are very close by. So because the red giant star has a lot of stuff off of it, a lot of material gets transferred from the red giant over to the white dwarf. And eventually the white dwarf is surrounded by a disk of material and on loan from the red giant here. So the two components actually go around each other because they're like barycenter about every 228 days. The orbit is circular and inclined by 67 degrees relative to us, though. But also, look at how close these two stars are only separated by half an astronomical unit, roughly about 45 million miles away. That's it. So you're able to, during outbursts from the red giant, be able to transfer this material. So as a result, during the outbursts here, the transfer of the material over to the hot white dwarf, the star becomes very bright for it. So you have this flash point. Here's the red white dwarf, the red companion star. So it's constantly transferring, and once you reach almost like a critical mass, it'll flash in a momentary flash of fusion. But it requires a critical mass, critical amount of material. So there's a period of time for that to build up. So it seems to be very, not quite clockwork, obviously, but this is what we're looking forward to seeing here. So this is it right here.
Is that the 1.4 solar masses?
Yeah,
Okay, so it's actually an atmosphere that is getting 1.4 solar masses, and then the atmosphere goes off.
exactly, exactly. So hydrogen rich. So this is what, excuse me, this is what we're after here. And then this is eventually what we'll see, a new star, a temporary star. Now, I have not read how long this new star remains bright. Have you read anything at all for duration?
No, I was thinking it was like 5 or 6 days.
About a week, yeah. I read that once, but okay, it's not a long time. So we'll see what happens, we'll see. That's all I have, folks, on this.
So the type 1A, the material is going onto the surface.
Yes,
The nova, it's going in an atmosphere, an envelope around it.
once you reach critical mass, so it takes a while.
So it's not temperature that makes it go off, it's the critical mass.
Correct,
Because the white dwarf is, you said 25,000 degrees.
yes,
There's no way that's gonna radiate that temperature to get up to millions of degrees where the nuclear fusion occurs.
exactly.
But it's the mass of 1.4 Chandrasekhar limit that we
Yes.
hit. And it goes off.
Perfect, yeah, very good. Anyone else?
So there have been some that lit up the night sky like
I didn't realize how small they
like
were.
the moon maybe.
Yeah, well, like the Crab Nebula.
Yeah.
Yeah,
And how long ago would that have been?
what was that, about,
1054.
something.
yeah, 1054.
Oh,
Yeah.
there were people.
Yeah,
on
it's
the
been a
scene.
while. Yeah, they documented it very well.
The
I wonder how
Chinese,
bright
I
it
think,
got. I mean, could you literally be
Yeah.
outside in the dark and
See it,
see?
you can see it in the daytime.
You saw it
Yeah.
today.
Wouldn't that be
The
something?
Chinese
Yeah, wouldn't that be
documented
something?
it,
Yeah.
That'd be
the
incredible.
Arabs
Yeah,
documented
that would be
It's
something.
nothing like that coming our way now, right?
As far as, well, they didn't know either, so,
Mormons
yeah.
conquered England.
But just think,
1054.
if you didn't know what was
It was
going
a good
on,
omen for them.
Yeah.
and suddenly there's this thing that you can see during the day like that. Well, I saw Ron in the forbidden place over there. Clearly, he did something wrong. He's angered the gods. Okay, so let's get Ron. And then it goes away. Hey, it worked. Everyone's happy. Wow.
Going through a volcano, right?
Yeah, right. Or Northern Lights, same thing. Or solar eclipse. You know, Christopher Columbus, on his 4th journey to the New World, he was running out of provisions, and he had an almanac with him. and the natives were not giving him stuff anymore. And he was waiting for rescue because his ships, his sailing ships, had wood boring worms, and he couldn't sail with them anymore. He couldn't go back to Spain. This was his 4th journey, so he's waiting. So meanwhile, he tells the natives, look, if you don't help me, he had an almanac, he knew a lunar eclipse was coming up. I'm gonna turn the moon red and anger the gods for you. Okay, so turned red, they said, okay, what do you want? Yeah.
Cleaned them out.
Yep.
Tecumseh did the same thing.
So,
Tecumseh.
yes, sir.
If, you said these neutron stars eventually cool down, so presumably there's some out there that have done that. Would that be detectable if we knew there was a neutron star and then didn't see it anymore, that there's a little place where you can't see anything behind it?
Yeah, you would, well, no, not a little place that you can't see anything behind it because it's so small. I mean, 12 miles across, it's not very much. But think of it, okay, just not in our lifetime, not in our Earth's lifetime, are we gonna see anything like that? It's just gonna take so long because they're just so hot, so high pressure. It's like even Earth, our core, think about it, for all these billions of years, our core is still hot. And because of the certain size, certain diameter that the Earth is. Look at cute little Mars, because its core has cooled down so much. So it takes a long time for things to happen. So, anyone else?
I don't know anything about any of this, but I like the pictures. But it looks so crowded that it looks to me like there could be a chain reaction and everything would just, boom, 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 boom. Is that possible?
No.
Good.
No.
Relax.
What does the neutron do to the companion star when it goes supernova? Well, it doesn't, when it explodes.
Well, I've never been there, but honestly, it's gonna flash big enough that there is gonna be some sort of effect, but you're still half an astronomical unit away. So if you think about if there's a big flash on the Earth, is it going to affect our sun? Yeah, but not much. So I think she was referring possibly to, let's see. Oh wait, keep going. You mean that one?
Yeah. It looks like they're all, if one little thing happens, they're gonna just
They're millions of miles apart.
chain reaction.
Much more than that, light years apart.
Light years apart.
Definitely, yeah.
Or not.
This is actually the same area in space as this. This is M11, the wild duck cluster here. And so all my students, all the researchers, I told them, you have to do some sort of a pretty picture kind of thing. She said, well, how about the wild duck? Okay, fine. So this was an early version of what she got, but I still like it, but the colors are wrong, but still, very nice. The wild duck, like in the 16-inch, that's a beautiful cluster. Very nice. But we were doing some experiments, even though it's a 12-inch scope, we wanted to see how far, not how far, but how dim could we go? What's the dimmest star that we could record in a 12-inch telescope? So long exposures, etc. And so we drew a line, because back then, this was 2007, the star catalogs up to magnitude 19.9, we had those, okay? But from magnitude 20 forward, it becomes exponential.
Oh, yeah.
And we didn't have those. So I said, let's go to magnitude 19.9. And that is what we did. So we decided, well, we'll just do monochrome, because with color, now you have to, exponentially expose so much more time. So we just said, we'll just stop here. So we got it, 19.9. So, not bad for a 12-inch scope.
How long of exposure was that?
Yeah, I forget. It wasn't that long. It was probably on the order of just an hour total. I'd say. So, but still, I just like it because of the very reasons that you point out. It looks crowded, but look at what we don't see. That's the amazing part there. So, anyway, anyone else? All right, thank you.